So we are still looking at sources of S2S predictability, so sub-seasonal to seasonal timescale predictability. Where do they come from? In this section, we look at tropical, extratropical interactions and teleconnections. So interactions are more direct. Teleconnections are kind of remote forcing. So it could be through waves or the indirect impacts through the jet stream and so on. Tropical extratropical interactions are actually quite interesting and produce very elegant solutions. Mathematically can be very heavy, especially when you get into barotropic and baroclinic instabilities and processes of eddies forming, eddies transporting momentum, energy, and so on. We will try to keep it as simple as possible. It's rather brief anyways. We can start by looking at the system in terms of let's say a zonal mean averaged over all longitudes meridional section, pole to pole, let's say in this case going from 40 south to 40 north. And I think most of you are aware of the basics, so depending on the season, ITCZ can be far north of the equator into the northern hemisphere or closer to the equator. There are lots of ideas about why it's asymmetric and so on. Nonetheless, given the asymmetry, you have the Hadley cell, so you have tropical heating, which is very critical for generating global circulation and part of the energy transport. So as you know from your basics in energy transport, we have more energy received in the lower latitudes than lost back to space, and it's the reverse at high latitudes. So the system is constantly trying to move energy from low latitudes to high latitudes, and Hadley cells are part of this energy movement. And we can see the heating creating strong rising motions which hit the tropopause or hit the ceiling when they are exhausted, when they have exhausted their energies, and then there is divergence in the zonal mean meridional sense towards the poles. So you have the northern hemisphere Hadley cell here and the southern hemisphere Hadley cell, and you get a subtropical jet stream where this termination happens. Without going into the details about Hadley cell termination, which is not really a fully understood process anyways, you have subtropical jet stream which is going to set off Rossby waves, which are going to also send eddy momentum fluxes towards higher latitudes. In the mid latitudes you again get the polar jet stream, which is very strong and very unstable, which begins to shed eddies and Rossby waves, etc., which can then come back to the tropics. What else can I say here? This is part of the meridional energy transport, even though in the lower latitudes, by the time you take the concept that actually you are moving moisture from cooler areas into warmer areas in the lower branch, more of the energy transport is done by the ocean in low latitudes, but let's leave it aside. But the ocean also has tropical extratropical interactions. Ocean by nature moves much more slowly, has a very high heat capacity compared to the atmosphere. So we have trade winds converging into the ITCZ. We have what are called subtropical cells, so upwelling Ekman divergence on the equator, divergence towards the subtropics, and then convergence in the subtropical gyres and downwelling, and then the return circulation. And then there is a very low frequency time scale global thermohaline circulation, which has this cross-equatorial cell crossing below the upper ocean STCs and going into the northern hemisphere. Obviously, Indian Ocean doesn't extend beyond about 25 north, so the MOC there, meridional overturning circulation, is different than the Pacific. This is just, you can think of it as the Pacific or the zonal mean in that case. So essentially the tropical subtropical connections are going to depend on how the tropical heating drives extratropical processes, and then how extratropical processes can then send energy back. There is a couple of chapters on this in the book by Peter Webster called Dynamics of Tropical Atmosphere and Oceans, and I have this course fully recorded on my YouTube channel. So I think it's chapter 10 and 11 that you can go and look at. Here we are just going to look at this figure as a summary of it. A schematic diagram of the interaction of divergent and Rossby wave domains of the tropics and extratropics. A heat source produces a divergent circulation transporting potential vorticity substance, which we haven't defined here, but this is the definition in the book, towards the poles. In turn, enhanced PV gradient supports a westerly maximum from which Rossby waves emerge. These propagate eastwards in a Doppler sense through the exit region of the jet, where distortion takes place due to shear and stretching deformation of the basic state. We will see a little bit more of that. Thus, distorted Rossby waves break recursively. This is important. It keeps happening. There is seasonality, but it's happening throughout the year, which gives us the time scales of S2S as we are focused on here. And flux the PV substance toward the equator, thus completing the circuit and fulfilling the impermeability theorem requirement, which we will not go into here. So here is a brief. That's latitude. This is longitude. So you have tropics, heating, divergent circulation, and you have the Rossby wave propagations. You have these different potential vorticity substance contours, let's say, and here is the Rossby wave dynamics in the mid-latitudes. I hope I'm doing this right. Yes. So this is latitude. So we have longitude. So we have certain places where energy is going from the tropics into the extratropics, where there is a mid-latitude jet. That's the PV substance. This is the zonal direction. So we have eastward propagating Rossby waves, which are recursively distorting and breaking. There is a cyclone on its way up the coast, so you can probably hear some winds. And that is going to pump energy back towards the equator in lower latitudes. You can see the distortion or the sloping of the PV substance contours. There are specific longitudes where the so-called westerly ducts or tropical upper troposphere trough in the eastern Pacific and the Atlantic oceans, where the reach of the mid-latitudes into the tropics is easier because of various properties that we will touch upon a little bit. Okay, so this is the main story of tropical extratropical interactions, how diabatic heating is very strong in the tropics and it drives global circulation. So it sends, you can think of it as Hadley circulation in the mean sense, eddy fluxes beyond that, subtropical jet streams forming. You can think of this also in terms of our thermal wind relation, where the energy transport and the equator to pole temperature gradient is got a horizontal density and temperature gradient, which gives us the strong vertical shear, and that vertical shear is a available potential energy. So that's baroclinic instability, which is converted into eddy kinetic energy. And there is also a meridional gradient because of this strong jet having poleward zonal wind speed differences going from easterlies to westerlies and then weak polar easterlies. That horizontal shear gives us barotropic instability, which also is converted into eddy kinetic energy. So there you are converting mean kinetic energy into eddy kinetic energy, whereas in the baroclinic instability we are converting mean potential energy into eddy kinetic energy. So the baroclinic barotropic instabilities are set up by the system itself because of the energy transport and angular momentum conservation considerations, which we are not getting into. But that's the dynamics of mid-latitude energy coming back and then tropical heating driving energy towards, not energy coming back, eddy fluxes coming back. Net energy transport always has to be towards the pole, right? Because you're going from energy excess region to energy deficit region. So I hope I didn't confuse that. Okay, so we'll visit some details as we go forward.